Wave behavior of electrons. So Louis de Broglie, he only died in 1987. I actually remember 1987. In 1924, he proposed that particles could have wave-like character in addition to their particle character. And this kind of sounds crazy, but we just finished talking last week about how light can behave as a wave and as a particle. So then maybe it's not so surprising that electrons, which we generally think of as particles, can also behave like waves. We see the wave nature of light most clearly in electron diffraction. And electron diffraction works a lot like light diffraction. We get an interference pattern. The pattern, though, is not caused by pairs of electrons interfering with each other, but by single electrons interfering with themselves. This is kind of mind-blowing. And I've got a video I'll show you in a couple minutes. So electron diffraction. This is proof that electrons have wave nature. So a beam of electrons produces an interference pattern the same as waves do. So when the light went through the slits, we saw this interference pattern of dark and light spots or stripes on this detector over here. And when electrons go through, they also make an interference pattern. If the electrons only behaved like particles, like, say, tennis balls that you're throwing at holes in the wall, the ones that went through would just go straight through and hit and make one stripe for each slit, and the rest of them would just be stopped by this barrier. That's what particles would do. But the electrons form the same sort of an interference pattern that light does. So electrons behave like waves, and we see this because of the diffraction patterns that they make. The wave nature of the electron is an inherent property of individual electrons. So de Broglie predicted that the wavelength of the particle was inversely proportional to its velocity, which gives us the de Broglie relation. The wavelength equals h, which is Planck's constant, divided by the mass times the velocity. So the faster it's going, the smaller the wavelength. So we can do problems like this. What's the velocity of an electron that has a de Broglie wavelength that's approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10th meters. Well, let's go back. Okay, Planck's constant. Do you remember Planck's constant? Oh, I'm writing with white. That doesn't work very well. 6.63 times 10 to the negative 34. Somebody's got notes. Remember what the units were? Do you have the units? The seconds or seconds squared?
Second squared.
Seconds squared. Okay.
And meters squared.
Kilogram meter squared per second squared. That sounds right. Okay, h. That's Planck's constant. And then this de Broglie, oops, it was 1 over the wavelength equals h over mv. Was it just the wavelength? Yeah, it was. Okay, that's screw up number 3 today that's been observed by students. I've done other screw ups. Thank you. I was just testing you to see if you remembered. So what do we need to plug in here? Here's h, right? H is 6.63 times 10 to the minus 34 kilograms meters squared per second squared. And down at the, that's a bad line. Down at the bottom, we need the mass and the velocity. The mass of what? What kind of a particle are we talking about here? An electron. What's the mass of an electron? And that's grams or kilograms? Kilograms. Perfect. So there's the mass. And what are we trying to find here? The velocity. So, okay, there's screw up number 4 because I just started putting numbers in here, right? So let's just start over. Because sometimes that's what you have to do. Okay, so we should really rearrange this first for velocity before we plug everything in. Otherwise it gets really ugly. So we have to be careful because we have a fraction on this side, and so it's best to cross multiply, clear the fractions. I'm going to change color for good luck now, that hopefully my brain's going to start to work. We're going to get lambda times m times v being equal to h. And then we're trying to get the velocity, so we're going to divide by lambda and m to make them go away. And then we have to do the same thing on the other side. So v equals h over lambda times m. Would it be confusing if I went up here and tweaked this? Would that be confusing? So basically what we've done is we've switched the places of lambda and v, right? So this is v, and this is lambda. Everybody okay with that? Thank you. So down here I'm going to put lambda. We're told that the wavelength is this number here, 1.2 times 10 to the minus 10 meters. Before we do the math, let's look at what's going on with the units here. Kilograms and kilograms, so those cancel out. There's a meter squared up here and a meter down here. So this meter is going to cancel one of those. And I think there's something wrong here. Because we should end up with meters per second, not meters per second squared. Yeah, I think it is. So what is that, screw up number 5? I'm going for a record today. Meters squared per second. This is why you shouldn't try to just pull things out of your head. You should look them up and double check. It's joules per second, right? Or joule seconds? Joules times second. So a joule is a kilogram meter squared per second squared times seconds, and that's where we get kilograms meters squared per second. So, watch those pesky units. So this one shouldn't have been there. So nice, we can just get rid of them. So what units do we have left here? Meters per second. And that works out pretty well, right? So let's do math. Oh, you did it for me? Thank you. 6.06 to the 6. That's a lot of 6s. And then the units will be meters per second. Any questions? I screwed that one up really nice. This is one of those calculations that we make you learn how to do, but most chemists never use this.
So it should be 6.1 basically, because we have 2 6 bits.
Yeah, 6.1. That's okay. I'll take that one. So that's number 6, right? Screw up number 6 on 6.06 times 10 to the 6. Sig figs. Darn those things. So this really isn't too hard. You just got this equation here. You've got Planck's constant. You just have to be careful with your units. If they give you the wavelength in nanometers or something, and they give you a mass in grams, and you got to get all your units to line up. The uncertainty principle. When you try to observe the wave nature of an electron, you can't observe its particle nature, and vice versa. It's a little bit like the Schrodinger's cat idea, where it's either dead or alive when you actually look at it. But when you're not observing it, it can be both, right? So the electron acts as a wave, or it acts as a particle. When we observe it, we force it to behave like one or the other. And that's what the uncertainty principle says. So its wave nature we see by the interference pattern. The particle nature we observe by its position, which slit it is passing through. And the wave and particle nature of the electron are complementary properties, meaning the more you know about one, the less you know about the other. So it's kind of frustrating because we want to know everything about everything, right? But you can't. You just flat out can't. So this is very interesting. So here's a slit experiment, right? And we've got the electron source going through. But if we shine a laser beam across here, we can tell which slit the electron is passing through because it's visible as it goes through the laser beam. When you shine the laser beam, you only get 2 bright spots, which is what you expect for particle behavior. You turn off the laser, and you get the spectrum, the interference pattern again. So by observing which slit it's going through, observing it behaving as a particle, because this interference is one electron interfering with itself. And so it has to go through one slit or the other as a particle. But as a wave, it can go through both. So any experiment in which we are trying to observe the electron results in the detection of a single electron particle and no interference pattern. And does anybody else just think that's kind of crazy? That you change its behavior just by observing it. A little bit like children, right? If someone's watching, they behave. Nobody's watching, they're tearing each other's hair out, right? Electrons are a lot like children. Or maybe children are like electrons. So Heisenberg's uncertainty principle actually quantifies this idea. The more accurately you know the position, the less you know about its speed. So here, x represents the position. Delta x represents the uncertainty of that position. V is the velocity. Delta v is the uncertainty of the velocity. M is the mass. So here's the uncertainty of the position times the mass times the uncertainty in the velocity. And that's going to be greater than h over 4 pi. So if this uncertainty goes down, this uncertainty goes up. If this uncertainty goes down, this uncertainty goes up, because this quantity always has to be greater than h over 4 pi. And I'm guessing you're not interested in the derivation of that equation, right? Bottom line, we cannot simultaneously measure the position and the location of an electron. Frustrating but true. Determinacy versus indeterminacy. According to classical physics, particles move in a path determined by their velocity, position, and the forces acting on it. We understand this because this is how objects that we can see behave. You throw a baseball, and where it ends up is a factor of the direction you threw it in and how hard you threw it, etc. So determinacy means that the present, what's presently true about it, determines the future. Its present trajectory determines where it will be in the future. Since we can't know both the position and the velocity of an electron, we can't predict the path it will follow. This is called indeterminacy. The future can only be described statistically. We can't predict where a single electron is going to go. The best we can do is describe a probability that an electron will be found in a certain region. And so this gets into a lot of statistical functions, and we draw a probability distribution map. So we can say, okay, in this region is where the electron probably is. So comparing electrons and baseballs. So classical trajectory, the pitcher throws the ball, it goes up in an arc, it comes down. He throws the ball consistently, and it's going to go into the catcher's mitt. For an electron, if you threw the electron, that's, if you could throw an electron, which you can't. But if you could throw maybe a little teeny, tiny person, right, could throw electrons like baseballs. Be a really, really tiny person. That reminds me of it reminds me, there's this band called They Might Be Giants. Have you heard of them? And they have this awesome song called Particle Man. Particle Man, Particle Man. And it says, does he get wet or does water get him? I'll find it and play it for you during lab. Anyway, so Particle Man's going to throw an electron, right? Even if he threw it exactly the same way every time, it would not follow the same path. We can't really predict where it's going to go. This does not make sense to us, but it's what happens with the very small. So you throw the electron the same place, same way every time, and it goes different places. So here in the middle, I can't see that. There's 20%, 40%, 70%. But 30% of the time, it's out here somewhere. And so we cannot predict where it goes. So the quantum mechanical strike zone. The number of particles is going to be highest near the center, and it's going to fall off as you go out.